So I put some material, actually David uploaded some material that's supposed to help you with the double layer a little bit, and I think on steady state you should have that part too. Let me know if there's a problem. So last time we talked about different stuff, but in the end we discussed the double layer, and so if we are talking about our standard electrode, and then this is solution, and we discussed that if we adopt this serial connection of the capacitor where this is a C double layer and this is a C Goey-Chapman layer where this is diffused part, and this is this tight ordered part, Helmholtz. Then 1 over the C double layer is equal to 1 over the C Helmholtz plus 1 over the C Goey-Chapman. Okay? And we discussed that this is pretty much proportional to 1 over D, where this is this distance or the width of the Helmholtz layer. There's an inner outer Helmholtz plane. I'm just going to round this up in just the distance that we assume is from the electrode's surface, for which you have basically this tightly packed layer. And we said that this is a order of 10 to 50 microfarads per centimeter squared, depending how we calculate the electric constant of water and what we take here for a D, right? And then we also talked about Goey-Chapman layer, which is proportional to the constant K, which is proportional also to the eta R. Then there is some K, which is called inversed by length, and then cosine hyperbolic, and then there's here 2kt, and here is the E minus E PZC, right? Something like that. Maybe I missed some term, but you can catch. And then, because of this inversed by length being proportional to the square root of concentration of our electrolyte, we talked about that at high concentration this is large and bigger than this, but in this configuration where we have parallel capacitors, then this term drops to 0, and then eventually Helmholtz layer is the one that is mainly contributing to what we measure as a double layer. And if this is very low, then this is much bigger than this drops off, and then basically, so overall you understand how the math plays the game here in what we see as a dominant contribution. All right. And so why is that important? And before I just go for the next step, I just want to remind you that we discussed E as an applied potential. And we have E equilibrium, which is equilibrium potential, or reversible potential. That's the potential that we know that dissolution and deposition reactions are occurring at the same rate, so the net change on the electrode surface is 0, right? Then we also defined EPZC, which is the potential of zero charge. And that is the potential on the surface at which we have a disarray, and the net charge from the solution side mirroring whatever is on the electrode side is zero, because the probability of positive and negative charge is about the same facing the electrode surface. And what is important, we said, if we measure double layer capacity of our electrode surface as a function of the potential, and let's say we are looking this when we have the low concentration of the electrolyte, which means good Chapman layer determines the how this really looks like. Then we have something that really looks like this, and this minimum in a capacity, I'm going to call C minimum, is at EPZC, right? So obviously the double layer charge, which we can, or double layer capacity, which we can measure experimentally for low concentrations, obviously has some kind of a minimum. As I told you before, if this is very high, the Helmholtz layer is the dominant contribution that we measure, and that is basically potentially independent, right? It looks constant. So maybe looks something like this, but relatively potentially independent when this is a CH and this is a C for each other, right? So it depends what kind of concentration of the electrolyte we have in solution. Now, for purposes of electrodeposition, what you really have to understand that we always want to have as conductive as possible electrolyte. There is some specific applications which we're going to discuss later on, which is a bipolar deposition, which we actually want to have a low conductivity for a particular reason. But in this case, in general, when we do regular electrodeposition, we want to high conductivity of the solution because we don't want to have any ohmic drop. So if this is the solution resistance, we want to have this low. So if you have plenty of ions in the solution, ionic conduction through the bulk of the solution is pretty good. And most of the charge or resistance that we see associated with the surface is related to either instant charging, discharging of the double layer, or actually our electrochemical kinetics happening, deposition kinetics. So we try to keep the solution as conductive as possible, meaning that supporting electrolyte, whether you have 0.1 molar acid, 0.1 molar sodium fluoride, it's relatively high. And so if you would want to do the double layer measurement of this type of the electrolyte to figure out where the potential zero charge, good luck. You're not going to see anything because Helmholtz layer determines how the double layer capacitance looks like with respect to the potential, which is independent, right? Okay, so now to switch back a little bit and give you an anecdotal thing about electrodeposition. So for about good 100 years, from let's say 1850 to 1950, electrodeposition was essentially super important industrial process. Just to start with the copper refining, where you have raw copper obtained due to the chemical reduction of the ores, etc., and then you purify it in a sulfuric acid solution into 99.99%. In that process, you get some gold and silver as well, which is called cathodic mud, to the point where you have a very important industrial process such as aluminium production, where you actually melt the salts. That process occurs about 800 degrees. So you have molten salt solution of aluminium ions with some carbonates or whatever. And then you apply the current where your electrodes are carbon, and you start depositing aluminium metal, which is a super important process, right? Then you had a lot of decorative applications like gold, where, you know, instead of having this made out of pure gold, you plate a few microns of gold and surface appearance is about identical as the gold-plated material. The difference is in density. You know, this is a steel coated with gold. Density is much lower than the real gold. So people used to use that a lot to cheat. I don't know if you've ever seen original golden coins minted in the United States, this golden eagle and stuff like this. Well, you know, it used to be the dollar had its gold counter value. And it used to be that you can buy for $1 anytime in a bank a gold at certain weight, because the dollar value was tied to the gold standard. It's like a Swiss franc today. And it used to be that, you know, the mint, Federal Mint Reserves, they would release golden coins, which had a value, I don't know, depending on the weight of the coin. And so that was common practice. Now, fast forward, and those were different coins, you know. I'm just giving you an idea that, for example, today, if you have a pure ducat, you know, coin gold, and if it's not having some historic value, which is, you know, whether it's minted in 18th century by Napoleon or, you know, by some Indian Shah, whatever, or, you know, so it's just the value of the gold. If you put it on the balance, it's a 99.9% gold, and it weighs 15 grams times about $1,300 per gram. You know immediately what kind of money you're going to get if you go and want to sell this as a gold, right? But, you know, most recently you can see that there's a lot of these crooks on the internet showing beautiful pictures of the golden coins and say, oh, just buy it, it's only $50, it is. And the story is written in such a way that you really almost think I'm buying a golden coin. Somewhere with the super small letters, they say actually that you're not buying a golden coins, but you're buying a coin, which is probably some nickel, steel, alloy, whatever, and they're plated with that much, or, you know, 50 microns of gold coating, right? But they tell you it looks identical. It's a re-release of the identical historic golden eagle coin, which, by the way, costs maybe $20,000 today because it's pure gold and has some historic value. And this one you can buy only for $200, for example. And so, in that respect, you know, there's a lot of electrodeposition business involved in forging different types of the coins. Then, you know, there's a lot of electrodeposition of the silver because it's the same type of the purification, you know. There's a lot of the electrodeposition involved in car manufacturing where you put chromium layers to protect from corrosion, or nickel chromium, you know. There's a lot of electrodeposition involved in the different kind of you know, beauty industry, like, for example, in some great extent also in some medical implants, which, you know, if you don't have money, you buy stainless steel implants and somebody goes and puts some gold coating on it, and those are much safer than stainless steel implants because the gold is hypoallergic metal, doesn't create any reaction from the body and so on. So the electrodeposition in general has been spread to a lot of areas, but most importantly, the golden age of this, besides this traditional dinosaurs technology, starts somewhat later after 1950s, because 1950s already or the age when the theoretical consideration which we are discussing here starts to catch up with the experience-based knowledge, and the people were able, through mathematically defined expressions, relate experimental observations and you know, parameters of the process. And what is important, and why I'm giving you all this intro, is that at one point this anecdotal knowledge starts to be dismantled. Why? Because, for example, when I went to Seagate, there was anecdotal knowledge involved in electrodeposition of magnetic alloys. Now, there was a lot of real science in that involved, but when I went there, they told me, this is how it works. Don't ask me a question. You have to do this, and this way. You have to put this additive and stuff, and it turns out you're getting a magnetic alloy which is really superior. There's no way you can create this magnetic alloy with any other process. Why is that? He doesn't know, but if you listen to him and do exactly what he tells you, that's what you get. Turns out that actually everything could be explained reasonably well, or at least you can anticipate the results based on what you're doing. And for that reason, I teach this class to dismantle this myth and nonsense that were floating around with some mathematically defined science that we try to accommodate here, so you can actually have an idea where the things come from and how this actually matches with our expectations. Okay, so additives in that anecdotal sense were just basically chemicals which, for example, if you have rough deposit, that's one of the first use, and you add some additive in the solution which already has an ions and stuff, this rough deposit will become relatively smooth, and that smoothness gave a bright appearance to the surface, and we call them brighteners, right? And this was important for these decorative applications, plating nice looking gold, silver, etc., right? But more importantly, for example, in a business where you need some coatings which need to have some hardness, for example, you needed to use certain type of additives besides some other things that you need to do. Also, for example, one of the key issues when you have a thin films in general with any kind of a deposition is that if you look into the stress as a function of the thickness curve, usually it starts really like small compressive stress due to nucleation, then there's a huge tensile rise, and then the stress kind of either stays constant or starts to decay. And for the most of the material of our interest, which have a low surface mobility of the atoms, it stays really high tensile. And this is of order of, gigapascals sometimes, or a couple hundred megapascals. And what happens is that you do electrodeposition, you have good adhesion at one point when you're growing the film, it delaminates. And that limits any kind of application of your film, right? So electrodeposition in that sense suddenly appears like a magic, because if I do without additives, I get this. If I get with additives, I get something like this. And absolutely no other deposition method kind of competes effectively with electrodeposition when it comes to stress management in the alloys or deposit. And this magic comes from the use of additives, for example. And adding to this story, for example, this magic has helped not only to keep the stress under control, but also stress is a property that alternatively could be affecting magnetic properties, anisotropy, etc. And so it turns out with additives you always get super soft magnetic alloys which are in demand for magnetic recording applications, flux guides, whatnot, right? So it turns out that this additive thing is giving you competitive advantage, but it was poorly understood until maybe I showed up. And another thing which is super important is another boost in these applications of electrodeposition for high tech started with the IBM, and this is a company that I have to acknowledge, where some smart electrodeposition guys develop technology as an electrodeposition controllable for magnetic recording application. They developed tools, meaning plating cells that can handle whole wafers. And more importantly, they also developed a process which is called superconformal electrodeposition or superconformal filling. And that has been used for copper damascene, which means it works like a magic if you have a profile like this, right? And this is the copper seed surface. And you have a specific design of the chemical bath, which is very important for you to understand specific design, meaning specific additives, etc. When you start plating, instead of getting conformal growth, eventually looking like this, and eventually closes here before it fills this, which would you expect from electrodeposition? Or maybe get these edges growing faster due to the field concentration and close this and with a void inside, which is something to expect from the physics of the field distribution. What you really get is that this gets filled up and you end up with even an extra bump here with copper. And then you CMP or chemically mechanically polarized, and this is your copper lead. And that's what the 99.9 electronics today, meaning integrated circuits, transistors, or everything else is connected with these copper lines produced by electrodeposition. So that's the golden age that happened in the 90s, and magnetic recording industry also had really huge success with electrodeposited permalloy, cobalt, nickel, iron, cobalt, iron. And today, basically, those mature technology use electrodeposition as a standard processing step, right? And later on, there's a lot more applications of electrodeposition came, and that's why electrodeposition today is actually essential process not only for this mass scale application, as I said, you know, copper mining, thing like that, but also nanotechnology, because, you know, those copper damascene lines are 7 nanometers today. 7. Those are the chips that are being currently tested and eventually will show up at one point in the products. What you're buying today, if you pay top box, is the copper lines that I think are 22 nanometers wide. But the chips are already built and tested with 14, 11. What I'm trying to tell you, that's all lined up, and they just try to squeeze as much money as they can from certain generation of the products before they reintroduce a little bit faster and so on. Okay. So now I gave you enough pep talks so you understand that electrodeposition is well understood science, but also it has this magic competitive advantage over other processes because of the few examples I just mentioned. I didn't mention all of them. And having said that, for example, harder coatings, as we discussed, you can get by using electrodeposition at certain conditions where you create smaller grains. We discussed that. Larger overpotentials, right? That's super easy with electrodeposition. You don't do much difference. You just apply more overpotential. With other deposition method like evaporation, so try to accommodate these kind of things. It's not easy. You have to heat it up, get higher flux, etc. With sputtering. You know, those are expensive tools. Here you just, you know, have potentials that you crank it up and you are getting these conditions change at your will. If you need hard coatings, I don't know if you heard in mechanical metallurgy there's a Hall-Pitcher relation. Deposits which have a smaller grains supposed to be harder. That's because of the certain things that I'm not going to go into. So here, you know, at will you can grow copper, for example, which is harder, or softer, gold, just doing simple manipulation of the overpotential. But it turns out you can even change more situation at your advantage. For example, if you don't want to go with higher overpotentials, because that might create some complications with some side process, you add some additives and they do grain refinement and grains become smaller. And so all these examples that I gave you, we're going to discuss from the point of the science, how this works and why this works, and you're eventually going to get a clear idea of what you really do with additives. Okay. But before I go further, let's discuss additives in terms of the chemicals, like organic molecules in the solution, right? So, typically, what are the additives? Well, those are organic compounds, right? Carbon chain type of the molecules with few extra other atoms. Let me give you idea. You know, typical one is a saccharin. You know what this is? That's a sweetener, right? And it has the heterocyclic, it has a benzyl ring, and then it has a something like this. I think, let me see if I did it right. It's a long time since I looked at the structure of the saccharin. But it looks something like this. Yeah. Yeah, my memory is still good. And so you can see this is a heterocyclic ring. It has nitrogen, sulfur group, oxygen here attached to this carbon. Here is the benzyl ring and so on. It's used heavily for electrodeposition of magnetic alloys, for example. Then you have a PEG, which typically we call suppressor or leveler or whatever. And PEG is a type of a polymer which has this alternating keto group or oxygen in between carbons, and depending, you know, on the length of repetition of this thing, you know, it could have a molecular mass of 200, 100, 400, 800, 2000. 2000 is already not soluble in water, but, you know, it can have a large molecular weight. I think what we use in electrodeposition is between 200 and 800. All right. Then we have MPS, which is mercapto propyl sulfonate, and that's basically a thiol, which has this thiol group here, SH, and here's a sulfonate side, right? And that's used for superfilling in combination with the polyethylene glycol. Then we also have some of my inventions, let's say L-cysteine, which is the amino acid, basically the one that we have in our body. It's totally harmless, and it's basically SH, then NH, and then C, OH carboxy group. Then, what else, you know, I should mention? There's a lot of other exotic chemicals which I don't have to really. L-cysteine is just amino acids. This is a sweetener. This is a polyethylene glycol. Glycol basically is a polyoxy alcohol, and this is a mercaptan type of the compound. So what I'm trying to see with you guys to recognize that, you know, those are organic compounds, obviously, but you can see these organic compounds are usually have some other atoms besides carbon, like nitrogen, like sulfur, carbon, and oxygen. And more important, what you see here is that you have partially charged positive, negative here, because oxygen attracts electrons more from carbon. You know, I don't want to go into too much chemistry. Nitrogen here is partially negative because it has more electron from this hydrogen. This sulfur is partially negative. This is partially positive hydrogen, and so on. So you can see those are polar molecules that have a charge not equally distributed along the molecule, but concentrated around some of these, I'm going to say dissimilar atoms, like this one, negative, negative, partially positive, partially negative, partially negative, so okay. Same thing here with these oxygen and so on. Now, why is that? First of all, these molecules will not dissolve in the water as a polar annulite if they don't have these polar bonds forming, because the way that they dissolve is that the water molecule attracts to this partial charge, creates these hydrogen bonds, if you remember chemistry, etc., and eventually hydrates around this, and this molecule becomes stable in the water because the water molecules like him, because electrostatically they are kind of in a minimum energy state when they're all surrounding this, versus when this guy is not surrounded with molecules of water. Same thing here. So they have to be soluble. If you try to dissolve paraffin in the water, it's not going to dissolve. It's going to dissolve in benzene, right? Because paraffin is not polar. It's just a long chain aliphatic carbon, right? Carbon molecule. But these will dissolve, right? That's the first thing with additives. Soluble in the water, a lot of polar parts of the molecule where the charge is localized to certain atomic groups or atoms. Okay, that's number one. Number two, when we, very important thing, how we see if there's some kind of interaction between the, we're going to call this now additive, and our electrode surface. Do we see any kind of a sign that we should be aware that this organic molecule will come close to the surface, maybe absorb? Because if it's not on the surface, there is no magic, because this organic molecule only does some kind of a magic thing if it's on the surface when you do electrodeposition. If it's in the solution, never comes close to the surface, what's the point? It's in a bulk solution, right? So it has to be in the proximity of the electrode, very close to the surface, absorbed, so it does its magic, right? So if you do now again your double layer measurements, and this is potential, and now you can have a higher concentration of the electrolyte. Okay, without any additive, the double layer capacitance will be almost constant, right? Why? Because this is basically like a Helmholtz layer, not really dependent much on the potential. But then I start adding some organic molecule in certain concentrations. As I keep adding, I'm going to see a little bit like this. Then, with higher concentration like this, then like that, and eventually really like this. So the capacitive double layer will start showing its dependence on this presence of this chemical in the solution, and then more likely you will see that this called capacitance well, where we see the minimum basically, will be around PZC, and it's going to show decrease. This level of C minimum will be going this way with increasing concentration of the additive, but also it's going to be widening up, right? Now that's textbook example. In reality, systems are very difficult to measure if you have hydrogen coevolution with with this kind of measurement. So in reality, it doesn't look so pretty as I draw, but that's the signature that your additive actually is interacting with your electrode surface, meaning absorbing. Now, if I now consider, for example, not this potential, but let's say here this potential, and I now plot C double layer as a function of the concentration of the I'm going to call this AD, right, of the additive. I'm going to see that at this particular potential that I'm looking at, this will be looking like that. And if I do this for a different potential, similar type of the surface, similar type of the plot will happen, right? Now, to fast forward a little bit, obviously we're talking about adsorption. Now, for this all, in general discussion, this adsorption I will assume that is well represented by Langmuir model. What the Langmuir model tells you is that the coverage of your adsorbate on the surface is equal to B times concentration of the additive divided with 1 plus B times the concentration of the additive. Now this B is the equilibrium adsorption constant, right? And this B is also a function of the potential at which we are looking at. So that's why if I look at the double layer, you know, capacitance is a function of additive concentration. It will not be the same if we measure at this potential, at this potential, at this potential, at this potential. Okay? All right. Now, going one step further, this functional, Langmuir functional, is a little bit idealized picture of adsorption, and it assumes that whatever adsorbs on the surface, which means these molecules of the additives, they don't interact with each other. They don't have any attractive or really repulsive interaction. So no interaction between adsorbed particles or molecules, but also any interaction with the substrate that might be stabilizing extra additionally the layer, meaning, you know, if the molecule comes this way or this way or this way, it's all excluded, you know, meaning as it comes, whether this way, it's the same thing, okay? Which is not true, but let's keep it simple. Now, if you plot coverage of this additive as a function of the concentration, what you're going to get is something that looks like this, where this is going to be 1. Maximum coverage of the additive on the surface is 1. That means the whole surface is covered by additives, right? At 0, it will be 0, obviously, no additives present. You can also see that if this is going to 0, this whole thing can cancel each other, and it stays 1 over 1, and this whole thing could be linearized, because 1 plus something very small is close to 1, and then you just have theta is equal B times A. So this part here, for very small concentration, is almost linear. It's like a B times concentration of the additives. And then you can see if I keep this bigger and bigger and bigger, then this whole term here is basically equal to this, and they cancel each other and it becomes 1. So it's an asymptote, right? Okay. Because sometimes Langmuir, to simplify the math, if we work with a small concentration, we just assume that it's linear form. Okay. This is just for you to keep in mind. Okay. So we have this, we have idea how the concentration affects the coverage of the additive. Now, now I'm going to tell you how we use our measurements of the double layer as a function of the concentration of the additive in general, or as a function of the potential, to extract the idea about coverage, right? So let me discuss this for a second. So if I have an electrode, and this is solution, I'm going to assume that at certain concentration and at certain potential, my coverage of the additive is just somewhere in between 1 and 0, right? It's not 0 because I have some additives to solution, but it's not 1 because I'm not exactly at this potential close to PZC, if you remember, where this is really small, but somewhere away. So what happens is that my additive molecule, and I'm going to call this A, forms some kind of a patches, and there will be a free surface. So the patches here normalized per unit area will be having area theta, and the free surface will be having area 1 minus theta, right? Now, this is just schematics. What you really know is that I have something like this, maybe, or maybe like that, or there's some molecules that have some structure, right? But this is just a cartoon for you guys, right? Now, when we look the electrode from this cartoon, we know that in this free surface that no adsorption has happened, we have a bunch of, let's say, positive ions, if this is a negatively charged surface, right, for example. We have a bunch of positive ions, and then maybe water molecules to oriented positive side towards the electrode, right? And then here I have organic molecules which adsorb. Then basically what I do, they displace these water molecules out, or these charged particles, and they kind of clog this part of the area because they're big, they have these structures and so on, and same thing applies, right? Okay. Now, if I just look this specific part here, now I can see that there's a different charge here, and there's different charge here, right? But if I want to, for example, calculate the overall, excuse me, the overall charge of the surface, I can say that my charge of the surface Q is equal Q1 minus theta plus Q theta, which means, and this is per surface area, so charge of this electrode is equal to the charge that belongs to the parts of the surface that are not covered by additives and parts of the surface that are covered by additives, okay? Since we are sitting at the same potential, right, using the very simple equation of the parallel plate capacitor, right, charge is equal to what? C times E, right? Is it or not? Okay. So then we can say that this is equal to, in this case where we have a free, I'm going to call this C naught times E plus, and here I'm going to call this CA, or maybe not CA, yeah, CA times E, right? Now, if I now want to normalize per unit area this charge, I have to actually have here this theta multiplying here and 1 minus theta multiplying here, because this doesn't apply for the whole surface area, it just applies for this part of the area where I have this, okay? And this is equal to, so basically what I've done, just express Q times E, right? Sorry, C times E. Now I can get rid of this E everywhere because it's a constant potential. We are looking this capacitance, and my measured capacitance here, C, will be equal to something which leads to the expression where theta could be calculated as C measured minus C A over C naught minus C A. So the coverage of my additive could be calculated from double layer capacitance measurements, which is this is measured. I'm going to call this measured. And this is capacity of the surface covered by additive. And this is capacity of the, and this is the difference between the capacity of the surface, no additive, and this is with additive. Okay? Now let's go back and do the measurement. So, yeah. Where? Yeah. See, no. See, no, and I'll explain. So this is the measured capacitance. This is potential. And let's say nothing happens when you add the additive, but then we have additive, and then looks like this. This capacity here is the capacity of the free surface. This is our C naught, right? It's a maximum value of the capacity. This capacity here is the capacity of the surface completely covered with the additive. It's a minimum. So this is the maximum minus minimum, C minus minimum, right? Okay. So what we really do when we study absorption of the additives on the surface is we study capacitance of the double layer as a function of the potential, and we see something like this. Here, obviously, somewhere will be EPZC, because the organic additives, I'm going to just explain you in a moment, always absorb within the region of the PZC. And then as you move away, the coverage has some dependence on the potential, which we don't have to explain right now, but the bottom line is this. You can see that just simply knowing this value and this value, and if I'm at this potential and I'm measuring this, see, I can say that theta here is equal C minus C additive over C naught minus C additive, okay? It's called Frunkin formalism or Frunkin expression for. Now, why is that? Okay, let me give you now back the story about this, okay? You know that this type of the surface, if you just look at the total capacity of the surface per unit area, now this surface looks like capacitors like this in series, right? Connected to the resistivity of the solution, right? And this is electrode. Now capacitor in series is C1 or CA plus C naught, right? Now, if we normalize per unit area, then it will be 1 minus theta C naught plus theta times C A, okay? It's the same kind of a thing that comes from going through the charge, but it just, you know, I use the formula for capacitors combination, right? And so, from this, you can always end up having this. But the question I'm having here is, why is the capacity of the double layer, when you have a covered surface with additives, smaller than capacity of the double layer when you don't have any additives? Let's have a look here. It's a huge molecule, let's say MPS, mercaptol, you know, has this SH group, and then there's a butyl part, and then there's a sulfo group here, right? When this molecule approach the surface, the adsorption happens through formation of this mercaptol, and so instead of hydrogen here, there is going to be metal surface. So this is an adsorption bond. This part of the molecule is the wetting part, which likes to be around the water. Okay? So the water molecule stabilizes this to be in solution, but this guy is binded to the surface. And it's a relatively large molecule. Now, this molecule have a very small dipole. If you don't know what the dipole moment is, P is equal to charge times the charge separation we call D. Now, charge separation is the distance between these two centers of the charges. So if this is partially negative, then this part here will be partially positive, where the carbon is, etc. What I'm trying to tell you, this is dipole. But this dipole moment has a relatively small charge separation. It's not like I have a negative ion and positive ion. And the distance here between them is small, right? So this whole molecule, when we look at the dipole moment, has a relatively small dipole moment. Which means in terms of the energy of electrostatic energy associated with this dipole moment in the electric field that is across the interface, we have a relatively low energy. Okay? Now when you have something like water, which is super polarized, remember, it's all negative oxygen on one side and positive hydrogens on the other, right? Water dipole is super strong, that's why you have these hydrogen bonds forming and so on. Or you have an ions, where ion, you can think about the charge separation between ion and the metal electrode surface is super small, and the charge on this value here is super large, right? That ion absorbing has a very high energy when it's absorbed. It likes to be absorbed, right? Now, obviously, this energy is a function, and energy is basically electric field. This is energy, so electric field, I'm going to just call E field times P, right? Polarization, or actually dipole moment. So, if I have a strong field across, which means I'm far away from the PZC, I'm here, there's virtually no chance I leave the organic molecule to be absorbed because the stabilization or reduction of the overall energy of the system is very small. The system doesn't gain anything by absorbing organic molecule when there's a strong field. Why? Because the absorption energy of the small molecule, like water or something else, in terms of the stabilization, is super large, right? So far from the PCC, I only absorb really, really nicely charged small particles which have a very high dipole moment. But as I decrease the field, suddenly this becomes super small, and something super small, times polarization, already is not giving you so much competitive advantage, because this thing, although much bigger for the small particles, in a very small field, this becomes close to zero. So virtually energy gained during the absorption between small particles and big particles is not so great. Suddenly, system can actually minimize its energy absorbing here big, molecules, because the field is so weak that actually the net gain in terms of the stabilization due to the formation of the adsorption bond is much better than the electrostatic energy that actually is satisfied by this whole business of adsorption. And that's why organic additives that we use in electrodeposition always do adsorb around the PZC, potential zero charge. Now, the logic to know where your additive adsorb is to first know where your PZC is. And your PZC you can always determine for your electrode by studying capacity as a function of the potential in a low concentration electrolyte. And then you get this. Then you know where the approximately PZC is. Then you can start adding your additives. You're going to see immediately, you know that they will be absorbing in that region there. Why is that all important? Well, let me give you an idea. If I aspire to have best action of my additives when I do electrodeposition, so this is the potential scale, right? And this is the reversible potential or equilibrium potential, right? This is the capacity of the double layer. And I determine that the PZC is here. Okay. If I go on the left side of my equilibrium potential and apply potential here or here or here, whatever, this will be my over potential, E minus E equilibrium, right? So if I'm applying over potential or potential at the electrode surface in such a way, or even if I run the current during electrodeposition where my potential ends up being in the region of PZC, and I have particular additive that absorbs on the surface in this solution, I expect to have creation of my deposit here on the surface. So I'm growing, nucleating, but on the surface constantly I will have also absorb organic phase. Do you understand that? If I apply potential here or here, I'm going to, so this is your absorb organic phase while I'm growing, deposit, which is always on the surface. But if I'm here, then I'm just having a regular electrodeposition with no any benefit of the additive. Okay? Now, again, why is that important? Well, first thing that you should know, we're going to discuss many other consequences, is that if you look the surface energy of the metal surface, pure, it's always much larger than the surface energy of the metal with adsorbed additive. Because if you think about the simple definition of the surface energy, this is the surface, and those are the broken bonds. If you remember the definition of the surface energy, this is half of the energy of the broken bonds. Those broken bonds on a clean metal surface are pretty high energy, so the surface energy of the metals are generally high, of order of 1 or 2 joule per meter squared, okay? Yet, when I have organic phase adsorbed, what happens is that some of these bonds will be saturated with this S, whatever, maybe this bond will be saturated with some oxygen from here. So there will be formed a lot of bonds with metal atoms, which will not look like broken bonds anymore of the clean surface, but will have a very different energy. And for that very simple argument, this surface energy of the adsorbate covered surface will be way, way smaller, okay? So that's the first consequence of the additives. Okay? How we do the time? Okay, I'm going to stop here, but this is very, very important for you guys to appreciate. Everything starts from here. When the organic phase is adsorbed on the surface, it changes the thermodynamics on the surface. So it's not anymore surface energy of the metal, it's the surface of the energy of the metal covered with organic phase. Totally different concept, totally different number. What that really means, nucleation is not going to be the same. There's some other processes we're going to discuss not going to be the same. But very important thing, when I have this situation here, I'm just going to erase this so you guys don't get confused. When I have this situation here, here's an additive you can think about covered layer of additive acting like some kind of a dielectric, right? So there will be some eta R1. It's not dielectric constant of the water for sure, right? Now, when you think about electrochemical reaction where Mn plus and E minus goes to M naught, this charge transfer from the ion to the metal reduction process happens when the ion comes really, really close, and eventually electron from the electrode tunnels into the ion. Eventually ion becomes an atom. It's an instant process and so on. And you remember we talked about that, but there is a free energy of the activation which is into the kinetics of the electrodeposition. We discussed Buttle-Warmer equation and so on. So we are changing the milieu or energy milieu by adsorption of additives for charge transfer process. Becomes more difficult, number one. Generally more difficult. Not necessarily always, but generally more difficult. That's number one. Number two, if the charge transfer doesn't occur so easily, or the energy barrier is much higher, that means in order to achieve the same deposition kinetics here, or Rm, and here, I will have to crank up the overpotential. But if I crank up overpotential to increase this, I also increase that. So kinetics of electrodeposition is going to be faster on these areas which are not covered by the additives than on the area that are covered. Now, over the time, what happens is that you have an additive, you have free surface. This grows faster than this. A small differential, but fast. Over the time, this surface grows like this, and this surface that is under the additive, I'm just going to draw the new kind of counter, but you know that the deposition of metal goes under the additive, okay? And then over the time, what happens is that this guy will be outgrowing this molecule of the additive, right? Because it grows faster. And this guy on the other side the same way. And once they overgrow this additive molecule in between, it will be effectively trapped, and we're going to have this covered by the deposit, where this organic molecule will stay in. And that does some specific stuff to the deposit. Makes it either better or worse. We'll discuss that. And the last thing I want to make you is that those additives like saccharin, those are molecules. At potentials we do electrodeposition, there's an electric field also acting upon them which are absorbed, which means some of these bonds here could be reduced. You know, this oxygen might become SO, and this oxygen might be, you know, what I'm trying to tell you, this molecule can be broken, meaning reduced. And then you might end up with some molecular fragments, and eventually you might form, in this particular case, metal sulfate particles as a side effect of electroreduction process of the additives. And this metal sulfate compounds stay in the deposit, and they do something to the deposit as well. And we're going to talk about that too. And so on. So the magic of the additive is not some myth or some kind of a anecdotal knowledge, but it's actually quite reasonably understood process if we keep close to fundamentals we discussed, and we look at this as a structured approach to understand what's going on. Now, I'm not saying this is maybe right away easily to comprehend, but if you really look this lecture at home, there's nothing here that is not logical. This is how additive works, and you will see the consequences of these few things then relate to the properties of the deposit. Sometimes good, sometimes bad. I have to tell you. But then these properties, if you know what you want, what you want to achieve, then you can manipulate and get better, deposit smaller grains, harder, who knows what, right? And so that's the science about electrochemical thin film chromatography when it comes to science and art of additives. Now, there's some other stuff we're going to talk about. There's a lot of stuff actually cannot be covered in one semester. But what I'm trying to tell you, if you do understand this thing, tomorrow you end up in Seagate and you get a job in a plating group, and they start telling you nonsense about this or that. Why? You know what it is. It's not that complicated. Of course, with experience, you can reconnect fundamentals with what you're really observing. You can even model and so on. In 4 years actually in Seagate, in every single bath I had in experimental production, because I work in research in Seagate, in every single bath I had, I knew my system so well because I had all the equations in place that I get in the morning the results where my technician comes and tells me saccharin is this much, some other is this much, and so on. I immediately put this into a computer, spits out. I know exactly what's going to be the position rate before they even tune and measure the position rate. I know where it's going to be. I know what's going to be coercivity, for example. I know what's going to be even roughness, everything. And by the time they qualify this, for example, the position bath for the real product, and they just keep bringing me measurement results, I look in my calculation and say, okay. That means you have control over the process when your calculations coincide with exact measurements. No unknown things, no unpredictability, nothing. Because of that, in 4 years, in electrodeposition operation, which when I joined Seagate, had a scrap, meaning a bad wafers, about 47%. After I left, our yield was 97.8. We only had a 2% scrap, and that 2% were not because we don't know what's going on, it was a human error induced, meaning I had some disciplinary issues which I had to deal with. And so that means you control the process, and everything starts from this type of the things, and you perfect it, and you know your system better and better, and eventually no unknowns, right? Now, we're not going to go everywhere in depth because that's not the point here, but we will mention a few here, there, things, I give you some papers to read, and hopefully some of that will stay with you, and eventually if you ever end up in Intel, and lithography group doesn't need you after 7 years, but there's an opening in the plating metallization group, and they want you, you will check your notes, and these notes will be enough for you to start on the right foot, okay? All right, I'll see you guys in about 15 minutes. We're gonna